So let me give you one other physics example of where this comes in, just so that you see it's not just this one example. So I'll just go through one of them in detail, and I'll just mention one other one. So there'll be two examples, but we'll only really cover one. So one thing you can do is do GG to Higgs, so Higgs production, where I measure a particular distribution, which is the PT distribution, PT of the Higgs. And it turns out that this process involves rapidity divergences. So let me try to draw one picture that allows me to capture all the different degrees of freedom. So here's, you could imagine that this is your top loop, but it's some short distance thing, and you can even integrate out the top. Think of it as an effective operator coupling two gluons to the Higgs. And so I'm in a frame, the center of mass frame of the collision. So these guys are back to back. So that means that one of them is n collinear and one of them is n bar collinear. So we have n and n bar collinears coming in, annihilating and producing a Higgs. And because of what we're measuring about the Higgs, we're only measuring the PT. If you think about what radiation you can have in the final state, well, you could have collinear radiation. So here's some collinear radiation. And that radiation has a small PT, so that's allowed in the final state. If we have a PTH distribution and we think about the limit, PTH much less than the mass of the Higgs, so there's some logs that you would want to sum, for example. So you could have collinear modes in the final state that would fit within this kind of kinematic setup, but you could also have soft modes. So soft modes have the same size of PT as the collinear modes, so they would be allowed, and this propagator here would be off shell. So it's an SET2 problem. Because you're only constraining a PT, then it's an SET2 problem with n bar and S. So PT Higgs, order MH lambda, and the modes are these ones. So let's get 2. And you'd want to sum, in this case, you'd want to sum up double logs of PTH over MH. That's what you might be interested in using the effective theory to do. OK, so you would go through the procedure of factorizing the cross-section. It's an inclusive calculation in the sense that basically in the final state it's Higgs plus X, right? Where X is collinear radiation or soft radiation. And it really the process is proton, for example, the Higgs plus X. So we would want to factorize the cross-section, amplitude squared. And here's kind of a sketch of how that would go. I won't go through the details. So you could think of starting with some operator where you've already integrated out the top. So you have a coupling of a Higgs to two gluons, and that happens in this gauge invariant operator with the field strengths. And then you would do the factorization procedure after you shift momenta sum over states. You can basically write that as a factorization for a matrix element of two currents. And you get some hard function, which is the Wilson coefficient squared of this operator. And then you get some operators that look like this, matrix elements that look like this. So there's some proton matrix elements where one of the protons is collinear, one of them is n bar collinear, and then there's a soft matrix element of some soft Wilson lines. They're actually in the adjoint representation. So I write transpose rather than dagger. These are adjoint representations. They should be in the same representation as the collinear fields, and the collinear fields here were gluons, right? So that when you go through the field redefinition, you would get adjoint Wilson lines for the soft if you went through an SET1, for example, picture, and then the G munus here would become the perpendicular polarization of the gluons. So these things here are going to give gluon PDFs. So basically, you have a factorization theorem that involves gluon PDFs and a soft function and a hard function. Now, if you look at this calculation, you have 3 modes. There's an SET2. They live on the same hyperbola. And you do have rapidity divergences in this calculation. So it's a story like this one. And I'm not going to go in too much detail, but just let me write down the factorization theorem for you with all the mu's and nu's explicit. It's really the same picture where the soft modes and linear modes need to live at different nu's. Same mu, and then there's the hard function where you have to run from one side to the next. So it's really this. You can keep the picture on the board. It's applicable to this example too. So if you calculate d sigma d, if you measure a rapidity of the Higgs boson, so I can call this YH, and you measure the PTH squared, the magnitude of the transverse momentum, there's some normalization factor, just kinematics. There's a hard function that only depends on the Higgs mass and mu. And then your other functions can exchange perp momenta, because the perp momenta of the soft function and the perp momenta of these linear functions are the same size. And what you're constraining is just the total. So the PT of the Higgs, if the initial guys coming in have 0 perp momenta, there's 0 perp momenta for the protons by design. So really there's a balancing between the final state radiation and the Higgs, which I can write like this. Okay, there's a delta function, and then you just have objects for the different guys. So do this in the proton center of mass frame. Because of the fact that we're measuring perpendicular momentum, it allows the PDF to be a tensor. But that kind of means it has 2 scalar PDFs in it. YH. And then there's a soft function. Okay, so it's kind of got the same type of structure that we were seeing in our previous example. The external kinematics actually fixes these variables here, which are like the x. This is like the Bjorken x. And the kinematics of the process actually end up fixing that when you go through the factorization. There should be a plus sign here. So the only thing that can change from the dynamics is the perp momentum. That's what gets exchanged between these guys. So you would sum logs by having normalization group equations for these objects. And you need them in mu and nu. The new one is always kind of simple because the alpha doesn't depend on nu, so it's very simple to integrate. You just get 1 log. But it's still an important thing because that 1 log is something that you can't get from the mu evolution. Okay, so these are called transverse momentum dependent PDFs. So they're not the standard PDFs that you're used to thinking about. They have this dependence on transverse momentum. And because of that dependence on transverse momentum, they also have these rapidity divergences. And these are the renormalized ones at this new scale. So there's a long sordid history of these guys. They were introduced in the early days of QCD, and people have really only sorted out very recently, both in the QCD literature and the SET literature kind of simultaneously and with different regulators, exactly how to make sense of these guys and define them properly and renormalize them properly. So this is kind of the last couple of years type stuff. So another example that we could do, which I won't go through in detail, so that was example 1. We could do an example that is not involving protons, but involving jets in E plus E minus. So we could do E plus E minus to dijets. And if we did something similar to what we did here, where we only measured a PT, then we would also be in this SET2 situation. So jet broadening is a variable B for broadening, where it's like an event shape like thrust, but you only measure perpendicular momentum. And what you measure are actually perpendicular to the thrust axis. So you still use thrust to get the axis for the jet, but then you don't measure anything like the minus or plus momentum. You just measure PTs. This would be another example, which is SCET2. And it actually would have, again, CN bar type modes, and you'd read a formula not exactly the same as this one, but again involving similar types of things, linear jet functions that depend on PT, soft function, some constraint between them. It's a little more complicated actually than this PT Higgs one, which is why I chose to write down the PT Higgs one. So I write that in my notes, but just because of time, I'm going to skip it for our discussion. So questions so far? So really, it's turn the crank once you believe some of the things I've told you. So something that might be interesting would be to work out, with mu evolution, we have constraints on the counterterms at all higher orders that you can write down by consistency of the anomalous dimension equations. And there's not, I don't think there's, to my knowledge, in the literature an expression like that for 2 loops, 3 loops. What would the various 1 over etas and 1 over epsilons, how would they have to work out based on consistency of the picture I've told you? I don't think anyone's done that. That would be kind of interesting. All right. So questions? None. Good. All right, so one final example.